Moving on now to passage number 3. Let's get started. The authors use the word backbone in lines 3 and 39 to indicate. Well, this one's specific, but I'm going to wait a little bit since this is line 39. I'm going to come back later. This question looks to be somewhat specific, but we need to find which sentence contradicts the claim made in the question. So we're going to skip this until we find something, until we get later in the passage. But 24 we can do, right? In the second paragraph, lines 12 to 19, what do the authors claim to be a feature of biological interest? So let's go ahead and let's read these two paragraphs. And what we're looking for here is what is a feature of biological interest? Okay, first the blurb. Okay. Watson and Crick deduced the structure of DNA using evidence from Rosalind Franklin and R.G. Gosling's X-ray crystallography diagrams of DNA and from Erwin Chargaff's data on the base composition of DNA. Okay, so little background info. Let's see. The chemical formula of deoxyribonucleic acid, DNA, is now well established. The molecule is a very long chain, the backbone of which consists of a regular alternation of sugar and phosphate groups. To each sugar is attached a nitrogenous base, which can be of 4 different types. 2 of the possible bases, adenine and guanine, are purines, and the other 2, thymine and cytosine, are pyrimidines. Why can't I say this? Pyrimidines. Okay. So far as is known, the sequence of bases along the chain is irregular. The monomer unit consisting of phosphate, sugar, and base is known as a nucleotide. Okay, some little intro. Now we'll get into this. We want to know what is a feature of interest. The first feature of our structure, which is of biological interest, is that it consists not of one chain, but of 2. Okay, that might be our answer. These 2 chains are both coiled around a common fiber axis. It has often been assumed that since there was only one chain in the chemical formula, there would only be one in the structural unit. However, the density taken with the X-ray evidence suggests very strongly that there are 2. Okay, so what is interesting? It's the fact that there are 2 chains and not one. That's choice D. We look at A, B, and C. That's not what's supported, particularly in the first sentence of this paragraph. So we go with D. The author's main purpose of including the information about X-ray evidence and density is to, well, this is a keyword question because even though we don't have a line reference, we do have these keywords, which we did actually just read. Right here is that discussion of the X-ray evidence and density. And why did they mention that? What was the purpose? To give support or to give evidence for why there is why they think there's 2 chains, or why they thought there was 2 chains. So establish that DNA is the molecule that carries the genetic information. The X-ray stuff doesn't help with that. Present an alternate hypothesis about the composition of a nucleotide. Nope. Provide support for the author's claim about the number of chains in a molecule of DNA. Confirm the relationship between the density of DNA and the known chemical formula of DNA. Okay, now, notice this part of the passage is all about the chains, and how the density in X-ray crystallography supports that. So we're going to go with C. Let's see, we just finished up to 19. Now, we'll wait a little bit more until we do 23. Based on the passage, the author's statement, if a pair consists of 2 purines, for example, there would not be room for it, implies that a pair, what? Okay, so let's go to 29 to 30. And we want to know what can be implied, or what is implied by this. So let's continue reading. The other biologically important feature is the manner in which the 2 chains are held together. This is done by hydrogen bonds between the bases. The bases are joined together in pairs, a single base from one chain being hydrogen bonded to a single base from the other. The important point is that only certain pairs of bases will fit into the structure. One member of a pair must be a purine and the other a pyrimidine in order to bridge between the 2 chains. If a pair consisted of 2 purines, for example, there would not be room for it. So what is implied by this? So all we know is the following, that in order to bridge the gap between the 2 chains, one member of the pair of bases must be a purine and the other must be pyrimidine. If there were 2 purines, there wouldn't be room for it, basically. Do they say anything about the size of them? Let's see. Don't think so. So let's go to the choices. By the way, with infer and imply questions, sometimes it's hard to come up with your own answer. Often I'll go right to the choices just to start evaluating that way. And I'll talk more about this in the video on inference and implication. Okay, implies that a pair of purines would be larger than the space between a sugar and a phosphate group. So if we go back to the discussion, the chain that makes up the backbone is an alternating of sugar and phosphate groups, but the pyrimidine-purine bridge is between chains, not within the chain. So A is not quite right. Implies that a pair of purines would be larger than a pair consisting of a purine and a pyrimidine. That seems reasonable, right? If there's not enough room for two purines, then and a purine and a pyrimidine fits, that must mean the two purines must be bigger than the pyrimidine, right? So this is kind of an implication, but it's also kind of obvious, right? It's, as we'll talk about, it's one step beyond what's in the text, right? If the two purines are too big and the purine and pyrimidine fits just right, then the two purines are bigger than the purine and pyrimidine. So that seems reasonable. Implies that a pair of pyrimidines would be larger than a pair of purines. We don't really know either way. Like, we don't know. I mean, it could be perhaps the case that the pyrimidines are larger, but we don't really know, honestly. All we know is that two purines together is too big. That's all we know. And a purine and a pyrimidine is just right. We don't know how the pyrimidines compare. And this is the same problem with D. Consisting of a pair consisting of a purine and a pyrimidine would be larger than a pair of pyrimidines. I mean, we don't know if that's the case. Maybe, perhaps, but there's not enough evidence. There's not enough evidence to support D in this part of the passage. So we're going to go with B. So we've just read up to 30. So let's go back to 23. A student claims that nitrogenous bases pair randomly with one another. Which of the following statements in the passage contradicts the student's claim? Well, we read earlier that they can't pair randomly. They have to pair one pyrimidine and one purine. So let's see. So 5 to 6, to each sugar is attached a nitrogenous base, which could be of 4 different types. Doesn't say anything about their pairing. So far as is known, the sequence of bases along the chain is irregular. So that's the sequence of bases along the chain. That doesn't say anything about how they pair with one another, though. 23 to 25. The bases are joined together in pairs, a single base from one chain being hydrogen bonded to a single base in the other. It doesn't really say whether or not they're random. So hopefully 27 to 29 works. One member of a pair must be a purine and the other a pyrimidine in order to bridge between the two chains. Yep, there we go. So D looks pretty good, so we'll go with choice D. All right, so 27 is about 47 to 49. The other 4 questions are based on the table. So let's go back. Let's answer 22 and read up to 39, and then we'll finish the passage and do the rest. So why does the author use the word backbone? Well, backbone is to describe the chains of the molecule. So let's see where they go with backbone later. We believe that the bases will be present almost entirely in their most probable forms. If this is true, the conditions for forming hydrogen bonds are more restrictive, and the only pairs of bases possible are adenine with thymine and guanine with cytosine. Adenine, for example, can occur on either chain, but when it does, its partner on the other chain must always be thymine. The phosphate sugar backbone of our model is completely regular, but any sequence of the pairs of bases can fit into the structure. This was blocked on the PDF, unfortunately. Like, it follows maybe from that or something. In any event, what's the point of using the word backbone? It's to show that there's a chain that holds together the structure, and then you have, of course, these bases that tie together the backbone. So let's see, the 2 chains, I should say. Okay, only very long chains of DNA can be taken from an organism with a spinal column. So don't just look at backbone and think spine. There's no discussion of spines or spinal columns anywhere here. The main structure of a chain in a DNA molecule is composed of repeating units. It seems pretty good. I mean, they do talk about how it's a sugar phosphate backbone, and here in line 4, it's a regular alternation. That's all right. A chain in a DNA molecule consists entirely of phosphate groups or of sugars. No, it's both, right? That's an alternation. Nitrogenous bases form the main structural unit of DNA. This is kind of true, but that's not why they're talking about the backbone. B makes sense when they're discussing the backbone. All right, 27 is about lines 47 to 49. So we're going to underline the words exact, specific, and complement. So exact, specific, and complement. And now we'll go ahead and read the passage and see why the authors use these words, how they function. Okay, it follows from that the long molecule may have many. It's hard to, with this blocked, it's hard to know what this says. It follows from that the long molecule, in the long molecule maybe, many different permutations are possible, and it is therefore seems likely that the precise sequence of bases is the code which carries the genetical information. If the actual order of the bases or on one of the pairs of chains were given, one could write down the exact order of the bases on the other one because of the specific pairing. Thus, one chain is, as it were, the complement of the other, and it is this feature which suggests how deoxyribonucleic acid may duplicate itself. So this might be important, right? It's to kind of show, why do they use these words? It's to show that this information is the carrier of genetic information, right? This structure, because it can be replicated perfectly, because these pairs always pair with one another and you can recover the code, it makes sense to show why this data is recoverable. So let's see. A, confirm that the nucleotide sequences are known for most molecules of DNA. It does not say that they're known for the molecules of DNA, just that they can be known. Counter the claim that the sequences of bases along a chain can occur in any order. This doesn't really say anything about whether or not the sequences can occur in any order. Again, it's just that they appear in a certain order that can be known, that can be understood. Support the claim that the phosphate sugar backbone of the author's model is completely regular. We don't really care about the backbone right now. It's about the bases. Emphasize how one chain of DNA may serve as a template to be copied during DNA replication, right? This is what's exactly mentioned in lines 49 to 51. Right, so there's your specific evidence that would point to why they're going to use these words. So we're going to go with D. All right, now we'll do the questions based on the graph. Based on the table and passage, which choice gives the correct percentages of purines in yeast DNA? So we look at our table, percentage of the different bases in different organisms. Here's yeast. We need to figure out which ones are purines, and I believe they mentioned this in the passage. Here we are. Adenine and guanine. So let's go adenine and guanine. So it should be 31.3 and 18.7. That's choice C. They actually flipped it around, 18.7 and 31.3. A little bit mean, but that's choice C. Do the data in the table support the author's proposed pairing of bases in DNA? And let's see. Well, the proposed pairing was, let's see, they set it down here. Adenine with thymine and guanine with cytosine. So does it support it? Well, what we would expect if they come together, if they pair together, they should be equal, their percentages, or pretty close. And let's see, let's just look at some examples. So notice that's equal, that's pretty close, it's pretty close, it's pretty close, right? So 20, 20, 17, these look pretty close. They're not exact, but they do look pretty close. Whereas on the other hand, 24 and 23, it's pretty close. 31 and 33, or 32 and 33 is pretty close. 27, 27. So they do seem to match up. So we will say that, yes, they're pretty close. They're not exact, but they don't really have to be exact. So let's just get rid of the nose. Let's say yes, because for each organism, the percentage of adenine is closest to the percentage of thymine, and the percentage of guanine is closest to the percentage of cytosine. Yep. So these two are closest, and these two are closest. And I'm guessing these mixes them up. Adenine and guanine, no. So this one's not going to work because we want to pair adenine and thymine with guanine and cytosine. So we'll go with A. 30. According to the table, which of the following pairs of base percentages in sea urchin DNA provides evidence in support of the answer to the previous question? Okay, so sea urchin DNA, we're looking for either 17.7 and 17.3 or 32.8 and 32.1. That would give us evidence for 29. That looks like A. Yep, so we'll go with choice A. Based on the table, is the percentage of adenine in each organism's DNA the same, or does it vary? And which statement made by the authors is most consistent with that data? So the adenine varies. I mean, Yeah, on the low end, we have 24.7. On the upper end, we've got 33.2. That's significant. So yes, we'll say it varies. Now we got to see which sentence supports that. Let's try D first. Just picking one randomly. It follows that the long run, many different permutations are possible, and it therefore seems likely that the precise sequence of bases is the code which carries the genetic information. So yeah, there we go. This part is suggesting that there's different amounts of each because you've got different codes of each. So that looks good, but we'll check the rest. 36 to 38. All it says in 36 to 38 is that adenine and thymine pair. Doesn't say anything about the amount of adenine. 25 to 26. The important point is that only certain pairs of bases will fit into the structure. Doesn't say anything about the amount of adenine. How about 6 to 8? In 6 to 8, all we're told is the types of purines and pyrimidines. It doesn't say anything about whether that will vary and how much it will vary. And so we see that in choice D. Oh, I don't know why I didn't see this. Yeah, so we can definitely get rid of A and B because they've got the same, both cases. We know it varies, and looking at between C and D, we know the best answer is going to be D. Even though this is blurred out a little bit, we have enough information to know that this is the part of the passage where they're talking about how the amount can vary because the code, the genetic information varies from organism to organism. Okay, so let's just check. We got 22, 23, 24, 25, 26, 27, 28, 29, 30, 31. We're good to go. Okay, next passage.